Hello everyone, welcome back to another video lecture. So in this lecture, we'll try to do a problem on bars of various sections. So in the previous video, we analyzed and we derived a formula for bars of various sections. Right? We'll see the question first. And this is the problem number 8. An axial pull of 35,000 newtons. It is directly given in the newtons, no need to convert into newtons, right? Is acting on a bar, right? The bar consisting of 3 length as shown in figure. So let me draw the figure here. So we are talking about bars of various cross sections, right? So in the question it says that on a bar consists of 3 different length as shown in the figure. So it looks like this. Let's say this is section 1, 2 and 3, right? And the length for section 1, the length is 20 centimeters. For section 2, the length is 25 centimeters, and for section 3 it is about 22 centimeters. Okay, if the Young's modulus is 2.1 into 10 to the power of 5 Newton per mm square. So right, Young's modulus is common for all these 3 sections because the material which is same, the material which is made up of this rod is same. This is a similar kind of material. So the Young's modulus is same. If the material is different, for suppose for your example, so this material of section 1 is steel and the material of section 2 is aluminium and the section 3 might be gold, then the Young's modulus will vary. So in the question he is asking to determine the stress in each section, right? So we have to find out stress in each section, and when it is applied for a axial pull, that means they are applying a axial pull, nothing but tensile load, right? Let's say P is the load. Now the second thing we have to determine, that is the total extension of the bar. So how much is the total extension of the bar? So that is going to determine in this problem. So let us see the given data first. Okay. Problem number 8. So given data, right, let's see what is given. That is, first one is the axial pull. Axial pull P is given, that is 35,000 newtons. Next, the length of, so let me draw here once. Applied a axial pull load P is given, that is 35,000 newtons, right? Now the length of the section 1. So let's say this is section 1, 2 and 3. Length of section 1, let's say L1. So this is L1, that is given 20 centimeters, 25 centimeters and 22 centimeters, right? So the section 1 length will be 20 centimeters. So this is a rod, that means it is a circular section. So dia of the section 1, let's say D1, that is 2 centimeters, right? So if you convert this into mm, it will be 200 mm, and the dia is 2 centimeters, that is 20 mm, right? So this is for section 1. Now we'll try to find out the area of section 1 A1, that is pi by 4 d square, isn't it? So pi by 4 into 20 square, that will be 314.159 mm square, right? So this is all about section 1. Now we'll try to find out for section 2. So length of section 2, let's say L2, that is 25 centimeters. Convert into mm, it will be 250 mm, right? So now, so dia of section 2 D2 will be 3 centimeters. 3 centimeters is a dia, and if you convert into mm, it will be 30 mm. So the area of section 2, that is A2, will be pi by 4 into 30, that square will give rise to how much? 706, let me check, 0.85 mm square, right? So this is for section 1. Section 2, now we'll try to find out the length and the area of section 3, right? Yeah. So what is the length? Length is given in the question, that is section 3 L3 is 22 centimeters, that is 220 mm. Dia of section 3, that is D3, is how much? 5 centimeters. Okay, it is given in the question. So the of section 3 is 5 centimeters, which is 50 mm. Now the area of the section 3 will be A3, which is pi by 4 into 50 square. So what is the answer? 1963.49. If I am wrong, please correct me. Mm square, right? So this is for section 3. Now we'll find out stresses in each section. First we'll consider section 1. So let's say stress in section 1, that is sigma 1 equals to axial load, that is load by cross sectional area, right? Area of section 1. So sigma 1 equals to 35,000 newtons upon 314, which is the area of section 1.159, and the answer for section sigma 1 will be 114.408 Newton per mm square, that is the units for stress. So this is for section 1. For section 2, we'll find out the stress in section 2, right? Right? Stress in section 2, right here. So it will be sigma 2 equals to P upon A2, that is the load is uniform, that is 35,000 newtons upon area 2, we got 706.85. So sigma 2 will become 49.51 Newton per mm square, right? So this will be sigma 2. Now we'll find out for section 3. Stress in section 3, right? So that will be sigma 3 equals to P upon A3, right? Now P is 35 3 zeros upon A3. We got how much? We got A3, that is 1963.49. So which is 17.825 Newton per mm square. So this will be your sigma 3, that is stress in section 3. Now we'll find out the total extension, that means total elongation when this external load P is applied, that is axial pull is applied in this material. This material is having a different variations or different varies in cross section, right? How you find out the total elongation? We already derived that total elongation for this when we are analyzing this bar of various section. So by using that formula, we can easily identify the extension, that is total elongation, right? So now I can write here the second part of this question is total elongation or total extension. of the bar. So total extension is expressed in this formula, that is denoted by dl, that is equals to P upon Young's modulus or elastic modulus of elasticity multiplied by L1 upon A1 plus L2 upon A2 plus L3 upon A3. So by using this formula, we already know the area of each section and the length of each section, L1, L2 and L3. Put those value here. So that is dl equals to, we know the load, that is 35,000 newtons upon Young's modulus is given in the question, that is 2.1 into 10 to the power of 2.1 into 10 to the power of 5 multiplied by L1 will be 200 in mm, that is 20 centimeters upon 314, that is the area we got, plus 250 upon 706.85 plus 220, that is 22 centimeters, convert into mm, that is 220 mm upon 1963.49, right? So put this on your calci, please. Let me know the answer. So that will be 35 point, let elaborate this, 2.1 into 10 to the power of 5, and it will become 0.366 plus 3.536 plus 1.120, right? So now can you tell me the answer? So TL will be 0.183 mm. So what is this? This is nothing but the total extension of this particular material, right? So now we'll see another problem with different material, right? So this is a problem number 9. Yeah, a member formed by connecting a steel bar to an aluminium bar. So it's a very interesting question. So a member formed of connecting two bars, that is, one is steel and another one is aluminium. That means here we are having different Young's modulus, different elastic modulus of elasticity value will be varying in this case, right? So it's given, assuming that the bar are prevented from buckling. So these bars are prevented from buckling, right? From sideways. Calculate the magnitude magnitude of force P that will cause the total length of the member to decrease, because here to 0.25 mm. Okay, the value of elastic modulus for steel and aluminium are 2.1 into 10 to the power of 5 Newton per mm square and 7.7 into 10 to the power of 4 Newton per mm square. We'll see the question first. It is given that a member formed by connecting a steel bar to the aluminum bar. So here two different materials are used for connecting this member. So assume that the bar are prevented from buckling. So it is a sudden change in shape when external compression load is applied on the material. So let me show you with the figure. So from buckling sidewise, calculate the magnitude of force P that will cause the total length of the member to decrease. So because of that compression load, the buckling will take place and the length will automatically decrease, and that is given in the question, that is 0.25 mm. The value of elastic modulus of steel and aluminum bar are 2.1 into 10 to the power of 4 Newton per mm square, and for aluminum it is 7 into 10 to the power of 4 Newton per mm square. So now we'll see the diagram so that you can clearly understand the given question, right? Here two different materials. In the question they will give the figure also, so don't worry about the dimensions and the length of the member. So let's say there is a P load is applying on the member, let's say P. So it is trying to buckle this material. That means because of this compressive axial load, this will buckle from sides. The length will decrease, just like compressive load. Okay, mainly we can see practically on our building columns, building members, or like columns, or yeah, the length is given, that is 30 centimeters and 28 centimeters. Okay, the dimensions are 5 centimeters into 5 centimeters Okay, steel, this is the steel bar, and this is aluminum, that is 10 centimeters into 10 centimeters. Aluminum bar, right? So now we'll see the given data. Once we'll write here, that is length of steel bar will be L1, and that is, how much is the length? 30 centimeters, right? If you convert into mm, it will be 300 mm, right? Next, we'll consider the area of steel bar A1, that is 5 centimeters into 5 centimeters. It will become 25 centimeters square. If you convert into mm, it will be 250 mm square, right? And we'll write the elastic modulus which is given in the question, that is elastic modulus for steel is given in the question, that will be E1 2.1 into 10 to the power of 5 Newton per mm square, right? Now we consider the length of aluminum section, that is the length of aluminum bar, that is L2, 38 centimeters, 380 mm. Area of aluminum bar A2 will be 10 centimeters into 10 centimeters, and it will become 1000 centimeters square and 10,000 mm square, right? This is the length. And what is the elastic modulus given for this? For aluminum it is given elastic modulus for aluminum, that is 7 into, that is, will denote it as E2, that is 7 into 10 to the power of 4 Newton per mm square. So this is the given data. For the both bars are made of different materials, right? So this material is made of steel and this material made of aluminum. Hence the total change in length of the bar is given by another formula we already derived in analysis of bars of various sections, right? So hence both the bars are made of different materials, right? One is steel and another one is aluminum. Hence the total change in length of the bar is given by equation. We already know that equation, that is dl equals to p, and the Young's modulus is different from for each material. For aluminum and for steel it is different. So L1 by E1 A1 plus L2 upon E2 A2, right? So this is the formula. Put the values here, you will get the answer. So dl is already given, the decrease in length. So because of this compressive load, they will be buckling from sides. So almost it will buckle somewhere like this, right? It will buckle somewhere like that, and there is a decrease in length. So how much difference is that? That is 0.25. It is given in the question, 0.25 into equals to P upon length is 300 mm for L1, and Young's modulus is given, that is 2.1 into 10 to the power of 5 multiplied by area is 2500 plus length L2 is 380 upon E2 is 4 into 10 to the power of 7 into 10 to the power of 4, 7 into 10 to the power of 4 multiplied by 10,000. That is the area, right? So now you will get it. That is P equals to, put this value on your calci, it will be 5.714 into 10 to the power of 7, 10 to the power of minus 7 plus 5.428 into 10 to the power of minus 7, right? Then P multiplied by, add on this, we'll get 11.142 into 10 to the power of minus 7, right? So that will be 0.25 into 10 to the power of 7 upon 11.142. So next, put the values here. So we got it 224,376.2341 newtons, right? So this is the load. P equals to, if you convert this into kilonewtons, right, that is 224.376 kilonewton. So this is the actual load here, that is 222.376 kilonewton. So this is how you can find out the load when the different materials are given in the question, right? So that's it for today's class. In next class we'll see few more problems on tensile load. So this is compressive load. We'll see different variations in sections, and we are going to apply some tensile load. Thank you so much for watching.